Section 7.1, Sequences. Part 1, Definition and Formulas for Sequences. Number patterns. An ordered collection of numbers or events is called a sequence, and we may look for a pattern to identify the sequence. For each of the following sequences, we will determine how to find the next term or number and state two more terms. So here's a sequence, 1, 3, 6, 10, 15. If I want to find the next term, I need to know what the pattern is. If I look here, to go from 1 to 3, I added 2. Then to go from 3 to 6, I added 3. To go from 6 to 10, I add 4. 10 to 15, I add 5. So the next term I'll add 6. So 15 plus 6 is 21. And then I'll add 7. 21 plus 7 is 28. Then I would add 8, etc. For this next sequence, 1, 4, 9, 16, 25, again, I have to look for a pattern. I can see that this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So following that same pattern, the next term would be 6 squared, or 36, and the next term would be 7 squared, or 49. We refer to the numbers in part A, these are triangular numbers, and the numbers in part B are square numbers. You might want to research why they're called triangular and square numbers. It's pretty interesting. Let's formally define a sequence. So a sequence is a function, f of n, with a domain of all natural numbers or a subset of consecutive natural numbers. So the natural numbers are 1, 2, 3, 4, 5, etc. So we're going to start with term 1, and then go to term 2, go to term 3. We don't have to start with term 1, though. It can just be start with term 3, and then we have term 4, term 5, etc. Now, some people do occasionally start with term 0. Normally, in this class, we'll start with term number 1. So a sub n, we can call that f of n. It is a function. We can also call it a sub n, which is just a convenient way to say that it is a sequence, not just any other function. And then the equation might call the nth term formula or the explicit formula. And it's often we use this notation with lowercase letter. Maybe if we have a sequence A, the next sequence we might call B, and we use a lowercase letter with a subscript. So the notations for this sequence, if we have the odd integer starting with -3, so -3, -1, 1, 3, 5, etc., different notations we can use for that. First, f of n equals 2n minus 5, where n is 1, 2, 3, etc. Notice if I plug in 1, I have 2 times 1 minus 5, which is -3. That was our first term. So the second term, if I plug in 2, I get -1. So -1 is the second term, etc. We could also write this with the a sub n notation. So a sub n equals 2n minus 5, n equals 1, 2, 3, etc. Another notation would be this with the curly brackets. So we have 2n minus 5. We start with n is 1, and we go forever. So it goes from n equals 1 to infinity. Or just 2n minus 5, and then it's implied that we're starting with term 1 and going on. A recursive formula defines the terms in a sequence by using one or more previous terms. So the first one or more initial terms have to be defined, and then a formula. So for this recursive formula right here, I'm going to start with the initial term, a sub 1 equals 2, and a sub n equals 5 minus a sub n minus 1, where n is greater than or equal to 2. So we already know a sub 1, that's 2. A sub 2 would be 5 minus a sub 2 minus 1, which is 5 minus a sub 1. So notice the n minus 1, that just means the previous term. And 5 minus a sub 1 we already said is 2, so we have 5 minus 2, or 3. So a sub 2 is 3. A sub 3 would be 5 minus a sub 2, which is 5 minus 3, or 2. And then a sub 4 would be 5 minus a sub 3, or 5 minus a sub 3 is 2, so we get 3. And a sub 5 would be 5 minus a sub 4, which is 5 minus 3, or 2. So this sequence starts with 2 and goes 3, 2, 3, etc., and actually goes back and forth between 2 and 3. So this is what the recursive formula looks like. Start with defining the first term, or maybe the first two terms, and then have a formula that has in there like the a sub n minus 1, which means the previous term, or an a sub n minus 2, which means the term 2 terms back. So let's find the fifth term of this sequence. I have a sub 1 equals 1, a sub 2 is negative 2, and a sub n equals 2 a sub n minus 1 minus a sub n minus 2. So a sub n minus 1 means the previous term, and a sub n minus 2 means the term before that. So if I want to find the fifth term, I have the first term, I have the second term, I need to find the third term. So the third term would be 2 times a sub 2 minus a sub 1, which would be 2 times negative 2 minus 1, or negative 5. And then a sub 4, I would have 2 times a sub 3 minus a sub 2, which would be 2 times negative 5 minus a sub 2, which is negative 2. So that's negative 10 plus 2 is negative 8. And then I can find a sub 5. So a sub 5 would be 2 a sub 4 minus a sub 3, which would be 2 times negative 8 minus negative 5, or negative 16 plus 5 is negative 11. Notice that to find the fifth term, I first had to find the third term, then the fourth term, and then the fifth term. So this recursive formula tells us how to go from one term to the next, but it wouldn't be very efficient if we needed to know, say, the 50th term, because then I'd have to go to the third term, fourth term, fifth term, sixth term, all the way to the 49th term, and that would take time. So the recursive formula is great, not always the most efficient. Let's talk about this sequence, the Fibonacci sequence. You may already know this pattern. We start with 1, 1, and then we add the two previous terms. So 1 plus 1 gives us 2. And then to find the next term, we add 1 plus 2 to get the 3. And then we do 2 plus 3 to get 5. So we keep adding the two previous terms. So how would I write a recursive formula for the Fibonacci sequence? I'm going to start by defining the first two terms. So a sub 1 equals 1 and a sub 2 equals 1. And once I have two terms, then I can write a formula for adding the two previous terms. So a sub n would be a sub n minus 1 plus a sub n minus 2. So adding the two previous terms. And then I need to specify that in this formula, n will be greater than or equal to 3, because we already have a sub 1, a sub 2, so now we're going to go on to a sub 3. The Fibonacci sequence has been around for a long time. We have evidence that it's been known as early as 200 BCE in India. It appears a lot in nature. So this sequence, we can see it in the number of petals on a lot of flowers, branching in trees, snail shells, lots of other examples. And it's named after the Italian mathematician Leonardo of Pisa, who was also known as Fibonacci. And one of the contributions he contributed to the field of math was the concept of zero. He helped with that. An explicit formula for the Fibonacci sequence exists. It's kind of complicated. This is the explicit formula for the Fibonacci sequence. So if I wanted, say, the 100th term, I could plug in 100 for n, and that would give me the 100th term. I wouldn't have to use the recursive formula and find the first 99 terms in order to find the 100th term. So what exactly is an explicit formula? An explicit formula will define each term in a sequence by using that position in a sequence, not by using the previous terms. So for example, here's an explicit formula. If I have a sub n equals 2 to the n, I can find any term I want. I can find the first term. So the first term, a sub 1, would be 2 to the 1, which is 2. A sub 2 would be 2 squared, which is 4. A sub 3 would be 2 to the third power, or 8. A sub 4 would be 2 to the fourth power, or 16. And I could keep going, but what if I just need the 10th term? Then I don't have to find the terms 1 through 9. I can just find the 10th term. So a sub 10 is 2 to the 10th power, which is 1024. An alternating sequence goes back and forth between positive and negative. So the terms alternate between positive and negative. Here's an example of an alternating sequence. Notice that we have a negative 1 raised to some power. So when n is odd, negative 1 to an odd power is negative 1. And when n is even, notice negative 1 to an even power is positive 1. So this will go back and forth between negative and positive. So let's write out the first 5 terms. So a sub 1 would be negative 1 to the first power over 1 plus 1 times 1 plus 2. Negative 1 to the first power is negative 1. So we have negative 1 over 2 times 3. Then the second term would be negative 1 to the second power over 2 plus 1 times 2 plus 2. And negative 1 to an even power is positive 1. So this term is 1 over 3 times 4. The next term, a sub 3, would be negative 1 to the third power over 3 plus 1 times 3 plus 2. And negative 1 to the third power is negative 1. So I have negative 1 over 4 times 5. A sub 4, we'd have negative 1 to the fourth power over 4 plus 1 times 4 plus 2. And hopefully you're starting to see this pattern. Here we have 1 over 5 times 6. So we have negative 1 over 2 times 3, 1 over 3 times 4, negative 1 over 4 times 5, positive 1 over 5 times 6. So this is an alternating sequence. It's going back and forth. And then a sub 5, it says to find the first 5 terms. So a sub 5 would be negative 1 to the fifth power over 5 plus 1 times 5 plus 2, which is negative 1 to an odd power, divided by 6 times 7. Find an explicit formula for the nth term of this sequence. So here we have a few terms. Here we have 4 terms. And we want to find the explicit formula. So we want a sub n equals something. So I'm going to look at this pattern. They're fractions, and the numerator is always 1. So I'll put 1 in the numerator. Then the denominator, we start with 1 times 2, then go to 2 times 3, then 3 times 4, etc. So term 1 has a 1 times 2. So I'm going to say, okay, term 1 has 1. So I'll start with n. And then 2 is 1 plus 1. Let's see if that works for the next one. This is the second term. So if I plug in 2 for n, I should get 1 over 2 times 3. And if I plug in 2 for n, I do get 1 over 2 times 2 plus 1, or 1 over 2 times 3. So then once you have an equation, you can look at some of the terms and make sure your equation is working for all the terms in your sequence.